You ever look at a skyscraper and just wonder, how does that not crumple? Or how can a steel rope, lift a 10-ton truck? Well, the answers aren't magic. They're actually hidden in this microscopic tug-of-war that's happening inside the solid materials all around us. So let's dive into this and uncover the hidden physics that literally shapes our world. Okay, so here's our first puzzle. It's something you've probably seen 100 times. A huge crane lifting some incredible weight. But why is it steel rope made of all these braided thin wires? I mean, wouldn't a single solid steel rod just be stronger? Let's find out. Next up, just picture any bridge or building being built. You're going to see these iconic I-beams everywhere. It kind of seems like a weird shape, right? Why not just a solid square or a circle? Well, there is a brilliant reason, and it's all about fighting gravity in the smartest way possible.
And for our last puzzle, let's think big. I mean, really big. Why isn't there a mountain on Earth that's, say, twice as tall as Mount Everest? What invisible force puts this hard limit on how high our planet's peaks can actually get? To answer all of these questions, we have to start with one simple, fundamental truth.
And here it is. This is the key that unlocks all of these puzzles. In basic physics, we often pretend objects are perfectly stiff. But in the real world, everything, and I mean everything from a rubber band to a steel beam, can be stretched or bent or compressed. And the way a material responds to those forces, it all comes down to two key properties. So on one hand, you've got elasticity. Just think of a spring. You stretch it, you let go, and boom, it snaps right back. That's its elastic superpower. But on the other hand, you've got plasticity. Imagine squeezing a lump of clay. It just stays squished. It's permanently deformed. And this is the cool part. Every material has a bit of both. It's got a point where it can bounce back, and then it's got a point of no return. Now, to measure all this stuff, physicists use this perfect cause and effect pair. Stress is the cause. Think of it as that internal tension you feel inside a rubber band as you're pulling it. And then strain is the effect. That's how much the rubber band actually stretches. So one is the internal force, the other is the visible result. Simple as that. So how many ways can an object actually deform? Well, the first one is the most obvious. It's called longitudinal strain. This is exactly what happens when you pull on a wire to stretch it out or when you stand on a soda can to crush it. You're just changing its length.
The second way is shearing strain. This one's pretty interesting. Imagine you have a thick book, and you push your hand sideways across the top cover. The book doesn't get shorter or longer, right? But the top face slides a little bit relative to the bottom. That tilting action right there, that's shear. And finally, we've got hydraulic strain. Picture dropping a solid block into the deepest part of the ocean. The crazy amount of water pressure squeezes it equally from all sides. It doesn't really change its shape, but its total volume shrinks just a tiny bit. That's hydraulic strain. Now, for most materials, as long as you're within their elastic limits, the relationship between all the stress and strain is actually beautiful and simple. It's called Hooke's law. All it says is that the more stress you apply, the more strain you get in a perfectly predictable straight line. Double the pull, you get double the stretch. And this graph, the stress-strain curve, is like a unique fingerprint for a material. Seriously, it tells us the entire life story of that material when it's put under force. It reveals all its structural secrets, from how flexible it is to the exact moment it's going to break. So, in the very beginning, you can see we have a perfectly straight line. This is kind of the happy zone for the material. It's the elastic region where Hooke's law is king. Any stretching that happens here is just temporary. You let go, and the material snaps right back, no problem. But if we keep pulling, we hit this critical boundary, the yield point. You can also call it the elastic limit. This is the material's point of no return. For something like the rock at the base of a mountain, this is the absolute maximum stress it can handle before things get, well, permanent. So once you go past that yield point, you see the curve bends. We're now in the zone of plastic deformation. At this point, even a tiny increase in stress causes a huge amount of strain. If you release the force now, it's too late. The material is permanently changed. There's no going back. If you keep pulling, you'll eventually reach the material's ultimate strength, and then it snaps. This is the fracture point. For a brittle material, like, say, glass, this happens really fast. But for a more ductile one, like copper, there's a lot of stretching that happens before it finally fails. Okay, so now that we've got the tools, stress, strain, and that all-important elastic limit, we can finally solve our puzzles. Let's start with the big one. Why can't mountains just keep on growing? So here's the deal. A mountain's own immense weight creates this enormous shearing stress at its base. Once a mountain gets taller than about 10 kilometers, that stress becomes greater than the elastic limit of rock. The rock at the very bottom literally starts to flow, kind of like an incredibly thick liquid, and the base starts to crumble and spread out. So yeah, physics itself puts a cap on how tall a mountain can get.
Amazing, right? Okay, let's tackle our second mystery. Those crane ropes. Why not just use one thick, solid rod of steel?
Well, this is just a piece of engineering genius. Sure, a solid steel rod, thick enough to do the job, would be strong, but it would also be incredibly stiff and rigid. By braiding lots of thin wires together, you get the same total strength, but you keep all the flexibility you need to wrap the rope around drums and pulleys. It's the absolute best of both worlds. You get strength and you get flexibility.
And that brings us to our final puzzle, the real workhorse of modern construction, the I-beam. Why that specific, kind of funny shape?
It's all about elegant optimization. To resist bending, a beam needs to be deep, tall. To handle the load on top, it needs to be wide. The I-shape brilliantly puts most of the material where it's needed most, at the wide top and the wide bottom, while getting rid of all that heavy, unnecessary metal from the middle. It's how you get maximum strength for minimum weight and cost. Just super efficient.
So when you think about it, from the shape of a bridge all the way to the maximum height of a mountain, what we actually see is a direct result of these invisible forces and limits. This tiny microscopic dance of stress and strain literally dictates the architecture of our entire planet and everything we build on it.
Which leaves us with a really fascinating final thought. We've just seen how the properties of rock and steel define what's possible today. So, what's next? What new materials are we going to invent that will push these limits even further, allowing us to build structures that right now we can only dream of?